We're in 11.7. Talking about area and volume ratios. So today we're going to talk about similar solids. For solids to be similar, they have to be the same shape. So a square, not a square, a prism can't be similar to a sphere. So they have to be the same shape. A triangular pyramid can't be similar to a hexagonal pyramid. They have to have the same shape. And all corresponding dimensions are proportional. And remember, proportional means the same ratio. So if we compare their heights, that would be the same ratio as if we compare their slant heights. That would be the same ratio as if we compare their base edges. That would be the same area as if we compare their lateral edges. So any corresponding dimension has to be proportional between these two. So for example, if we had a couple of rectangular prisms, which is another way of saying what kind of shape. A rectangular prism is a box. So we have a couple of boxes. Not drawn to scale. All right. And I'm going to say this is 8, 3, and 5. And this is 10, 4, and 7. And we want to know, are the prisms similar? If they are, then all corresponding dimensions have to be proportional. They have to have the same ratio. So we're going to match up the long side with the long side, the short side with the short side, and the medium side with the medium side. So I'm going to make a proportion 8 over 10. I can reduce that to 4 over 5. The other two sides, I have 3 over 4. And for the other two sides, I have 5 over 7. 4/5, 3/4, and 5/7. Are those the same? No. We can't reduce any. So these are not all the same. So that tells us these are not similar. So that's how we tell if solids are similar. Corresponding dimensions have to be proportional. Well, if they are similar, then we can figure out ratios of their areas and their volumes. So for area and volume, if the scale factor and the scale factor is the same as saying the length ratio, and we have two similar solids, so if our scale factor is A over B, so we make a ratio of corresponding dimensions. two slant heights, two radii, two base edges. And that ratio is A over B. The ratio of the areas is just like when we talked about two-dimensional shapes, A squared over B squared. We square the length ratio to get the area ratio. The ratio of the volumes is A cubed over B cubed. We cube the length ratio to get the volume ratio. So this is how our ratios of area and volume are related to the ratio of lengths. And the way we're going to apply this to solve problems is exactly like we did when we talked about similar polygons. We're going to end up setting up a proportion to figure out the missing pieces of information that we have. All right, questions on our relationships there? Okay, let's apply this to a problem. So we know the volumes of two similar solids. Is 40 cubic inches and 135 cubic inches. The surface area of the smaller is 48 square inches. What is the surface area of the larger? And here, it doesn't matter what the shapes are. We're not using a specific formula to find surface areas and volumes. All we need to know is that they are similar. And we have these ratios. So our plan here, let me write our plan. So we're going to have multiple steps. We're going to use the volume ratio to find the length ratio, because we know how the volume ratio and the length ratio are related, and they give us two volumes. We're going to use the volume ratio to find the length ratio. We're going to square it to get the area ratio, because we know if we have a length ratio, we square it to get the area ratio. And then we're going to use the information in the problem to write a proportion. All right, so let's do the first step of the plan. We know the volume ratio is 135 over 40. And we know that the length ratio is A over B. So the volume ratio equals A cubed over B cubed. The length ratio is A over B. Well, I have 135 over 40 equals A cubed over B cubed. How do I undo those cubes? We do it just like we did on our opener. We have to take the cubed root So we're going to cube root both sides. So what I'm doing is the cube root of 135 over the cube root of 40. And that's going to give us a over b. The cube root is going to undo the cube. Well, the cube root of 135 is 5.13. If I put that in my calculator. And the cube root of 40 is 3.42. Now we have the length ratio. So our area ratio we square the length ratio. So 5.13 squared over 3.42 squared. When I do that, I get 26.32 over 11.7. Now we're going to write our proportion. The area ratio is also, they tell us the area of 1 is 48. What do we want to call the one that we don't know? X. So the area ratio is also, and I need to do, I have larger to smaller. So I need x over 48. I want to keep my ratio in the same order. I did large over small on all of these. The area ratio is also x over 48. So now I can write a proportion. X over 48 equals 26.32 over 11.7. Those two area ratios are for the same two similar solids. To solve this, I'm just going to multiply both sides by 48. Those go away, and I get x is 26.32 times 48 divided by 11.7. And I get that x is 108 square inches. And this is the area of the larger one, the surface area. So it better come out larger than 48 square inches. That's a way we can check. Got a bigger number. So that tells us at least we didn't make a mistake that way. All right, questions there? So this is exactly how we solved this type of problem when we talked about similar polygons. We did the same kind of process. All right, let's look at one more. We're just going to do a different order this time. The surface area of two similar solids. Are 52 square feet and 208 square feet. The volume of the larger is 192 square feet. We want to find the volume of the smaller. So this is almost the exact same problem, except now this time we're starting with surface area instead of starting with volume. But we're going to solve this problem in the same way. So our plan. We're going to use the area ratio to find the length ratio. because we know how those two are related. We're going to cube it to get the volume ratio. Because we know we cubed the length ratio to get the volume ratio. And then we're going to write a proportion with the information that the problem gives us. I wrote plane. And what's funny about that is I was thinking in my head, don't write plane. All right, so let's start our plan. We're going to use the area ratio. Is, and I'm going to do small to large, because we end up wanting to find the smaller one. So small to large. The area ratio is 52 over 208. And we know that that equals a squared over b squared, where a over b is the length ratio. So in order to get the length ratio, I'm going to take the square root. So a over b is the square root of 52 over the square root of 208. I need to undo these squares. Well, when I take those square roots, I get 7.21 over 14.42, which is 1/2. The volume ratio. We know is a cubed over b cubed. So we're going to cube the length ratio to get the volume ratio. 1 cubed is just 1. 3 cubed is 8. The volume ratio is also the one that we don't know, x over 192. These two volume ratios are the volume ratios of the two same similar solids, so they have to be the same. We're going to write a proportion now. X over 192 equals 1 over 8. Multiply both sides by 192. Those go away, and I get x equals 192 divided by 8, which is 24 cubic feet. 24 is smaller than 192, which is good. We shouldn't get a bigger volume for a smaller solid. All right, questions? So this is the type of problem solving that you're going to apply these ratios to. And there's definitely a problem, something like one of these two on your test. Okay. Homework. Page 746, 6 or 28 even, and 32 through 38 even. Questions?